So yeah, the point of this is to sort of take the results of our experiment and put them together and come up with a formula. Now, this is not something that you're going to be able to do on your own by any stretch. And again, as always, if you want to just sit back and watch and then print out later, that's fine too. Yeah. Or if you want to try to write along as you can. If you get more engaged and sort of follow along by writing, then let's do that, okay? Okay, so that's just there as a picture to sort of remind ourselves of what the apparatus looked like. And for me, it's a visual, oh yeah, that goes with that lesson kind of thing. So, and I realize that you haven't completely finished the data, but you probably have a pretty good idea of what the graphs look like already. Alrighty, so what we're going to do is we're going to take the results of our experiment and derive some formulas that relate centripetal force, Fc, to various aspects of UCM. UCM stands for uniform circular motion. Uniform means that it stays the same. Okay, so the first part of the experiment was period versus centripetal force. In other words, this is the one where we change the number of washers. And the more washers we put on the bottom, right? When we added more washers here, that increased, if you got more weight here, you're increasing that centripetal force. Okay, so period squared versus Fc. When you graph the period squared versus Fc, your graph should look like that one. Is that what you got? Yeah? Okay, so that tells us that it's likely a inverse relationship. And you might remember that from like the first week or 2 weeks of grade 11. When you get that curvy down thing, that is an inverse relationship. This suggests that it may be an inverse, or it could possibly be an inverse squared relationship. Okay, because the difference in shape between inverse and inverse squared, if that's inverse, inverse squared is just like that. So it's kind of hard to tell if they're not side by side, which one it is. Okay, and we already were graphing period squared, so it's already sort of likely inverse. So to confirm, we're going to take t squared and we're going to graph it versus, and I asked you to do this, 1 over Fc. We're going to create, we're going to literally flip the data and see if we get linear. Did you get linear when you did the second one? Sort of, kind of, maybe? So this suggests that it's likely an inverse or an inverse square relationship. So we're going to take t squared versus 1 over Fc, and when you do that, you should get straight line. Right? This confirms our suspicion that t squared is proportional to one over Fc. The period squared is proportional to 1 over Fc. In other words, the bigger the centripetal force, Carter knows this, the more washers you put on, the faster it goes. Because when it goes fast, right, the t squared changes. When it goes fast, the t squared gets less. So t squared, the bigger the force, the less the period. That's what this means. Big force, small period. And remember, the period is the time it takes to go all the way around. And if it's a small period, then that means it's going faster. Yeah? Good? That's what you should have got out of that experiment. Part 1. T squared is proportional to 1 over Fc. What we're going to do is we're going to take all 3 of those, and we're going to put them together in one great big giant proportionality. I thought you were going to scream there for a second, but no? English exam, right? Okay, what did you get when you did period squared versus radius? Radius was the length of the string, right? You should have found that when it was short, it was the radius, or the period was what? really small, really fast, right? And the longer it got, the longer it took to go around. So you should have got a graph that looked like that, did you? Kind of? What sort of relationship does that imply? It's a direct or linear relationship. In other words, t squared is proportional to r. The bigger the radius, the bigger the period squared. We're always dealing with period squared. Okay, so we've got two parts of our big giant proportionality. Period squared versus mass. When you added more and more stoppers, what happened to the period? When you added 4 stoppers on the end, did it go really fast or did it go really slow? Remember? It would go slow. It would increase the period. The more stoppers, the slower it went, which would increase the period. So in other words, the period, it's a linear relationship again, although with only 4 data points, it's maybe not quite the best. And we are changing our apparatus too, so there's a lot of variables there. But for the most part, you should have gotten a straight line, which implies that t squared is proportional to m. The bigger the mass, the bigger the period, which means slower. Bigger mass, bigger period, in other words, slower. So I'm going to take all 3 of those and mush them together, mash them all up. By combining our proportionalities together, we get, and here's where it's going to start to get a little crazy, gang. T squared is proportional to Rm over Fc. I put the 3 and I put them all together. The period squared is proportional to the radius times the mass divided by the centrifugal force. Now, years ago I used to teach about how to convert proportionality statements into equations. I don't do that so much anymore, but I do sort of mention it. How do we go from proportionality to equation? We have to insert a number that makes it work, a constant, like the pi in C area equals pi r squared, right? You have to insert a number that makes it work. And so as an equation, this would become t squared is equal to KRM over FC, where K is the constant of proportionality, the number that makes it work, the pi in that formula. Maybe even K is equal to pi. Would that be possible in a sort of circular motion kind of thing? You kind of get the feeling maybe it's not exactly pi, but there's going to be pi involved. And someone always says, I like pi. And if not, then I say it. Flapper pie is nice. Ever had flapper pie? It's pretty good. Saskatoon. Yeah? I used to like lemon pie as a kid, but yeah, not so much anymore. Yeah. My grandma used to make just chocolate pudding pie. She'd get a pie shell and put chocolate pudding in there. It was good. Yeah. That's about the easiest pie you can make. So, we can rearrange this. What we're going to do is, because we really want a formula that gives us equal to centripetal force. So I really want this guy to be up there. But that means I got nothing down here, so I'm going to take the t squared and I'm going to put it down there. I'm thinking you guys can do that mental gymnastics now, that algebra kind of thing. No? I mean, all I'm doing there is like going like, 10 is equal to 20 over x, right? And I'm switching x equals 20 over 10. That's all I'm doing, just switching them. Right? So I'm going to rearrange this to, what's it going to look like? Yep. Fc is equal to KRM all over t squared. We want a formula that tells us the centripetal force. Okay. So now, what do you think our goal is? Like, what's the next step? Like, what do we want to find here now? This formula is no good unless what? Unless I know the value k, right? It's not going to be any good to us. So we got to work toward finding a value k, and you're not going to like this derivation. This is by far and away the craziest, most derivation you're going to see. Don't worry about duplicating it. Just sit back and be happy you can sort of kind of follow along.
So we don't have to stand.
Oh, no. I'm just showing you where it comes from. Okay? Yeah, this is, yeah. You're breaking new ground here. Okay. We're going to compare this to our very old friend from grade 9, F equals ma. And if F is centripetal force, then the A is centripetal acceleration. So that's all I've done here, right? Is I've taken Fc, centripetal force, equal to MAC. If we compare these two, right? There's M there. What does that kind of lead you to believe? Well, this AC is going to equal KR over T squared, right? Which is kind of why I put that FC up there. Okay? So we're going to predict that our formula for centripetal force is, why do I have it like that? I don't know. That seems weird. No, two of them. We're going to predict that our centripetal force formula is KR over T squared. And again, I'm going to get you to that T. What is that value of K? We're going to attempt to derive a formula to see if it matches our prediction and to determine the value of K. So we're going to by geometry, using nothing but our brains, we're going to try to come up with this formula. Okay, this is our prediction based on the data from our experiment and the shapes of the graphs that we came up with. And I'm obviously showing you the path. Okay, are you ready? I will. I'm not. Here we go. No. Okay. I would suggest sit back and relax. I never make you. I would suggest you sit back and relax. It actually helps me because then I can move like with some speed, kind of thing. In one complete revolution, would you agree that the distance traveled d is the circumference?
Yes.
Okay. And you remember from way back that the circumference is 2 times pi times r, right? From like grade maybe 7 or 8, right? So the distance traveled is the circumference, which is equal to 2 pi r. Okay. And the time to go around we call the period, which is t. Carter, please watch. You can't just be in the room while this happens. Okay. So given this, we're going to write the formula for speed, which is, or velocity, d over t. And that d is going to be equal to the circumference, which is 2 pi r, and the period is the t. So I'm taking v equals d over t, and I'm rewriting it for circular motion to be 2 pi r over t. So far, so good? Okay, not that challenging to there. Okay, then I'm going to flip. I'm going to say here now that's equal to v, right? And I'm just going to take the t and put it up there and put the d down there. And I'm going to come up with t equals 2 pi r over v, and I'm going to call this saved equation number 1. Put it on the mental clipboard. T equals 2 pi r over v. Sure. T equals 2 pi r over v. And where did that come from? It came through this sort of thinking process about the circumference and the time, right? No. We're not even close to k yet. Yeah, easy there, Joel. We're at least 15 minutes away from our value for k. Who's signing up for physics in university? Okay. On another line of thought. centripetal acceleration. Given that the formula for acceleration is that you remember from grade 11, A equals delta V over delta T. Okay, that's not new, right? We're going to rearrange that to delta V is equal to A delta T. Everybody good with that? And I'm going to say that for the entire revolution, the delta T is equal to the period. So I'm going to replace delta T with a big T. And the delta V is, I'm just going to relabel it as delta VT for total change in velocity, right? In one revolution, the total change in velocity in one revolution. So now I'm sort of just relabeling things, and I get delta VT is equal to A times big T. And we're going to call that saved equation number 2. That's all I've really done there is taken our old formula for acceleration, rearranged a little bit, and sort of relabeled for one complete revolution. And I'm calling that saved equation number 2. Does the big T in saved equation number 2 equal the big T over here? Guess what's coming? Eventually, right? People actually do this for fun.
Why would you do this?
People's definitions of fun are different. Yeah. I won't say that I'm doing this for fun.
You know the name of the guy who first did this?
No, I don't. I don't know who sort of came up with this. Yeah, no. No. But I do have a sense of, and I try to instill that, like I think that I personally, I have a sense of, I can look at this and I appreciate the ability to do that, right? Like I can follow this along. Could I come up with this on my own? Probably not. I hope that sort of when you're done, you can appreciate what goes into coming up with this, right? And say, yeah, that's kind of cool. I'm not going to do that for fun, but that's kind of cool. Okay. Here's the one that I really, really hate. And sometimes I just zip right through. If you don't, this is sort of another way to look at it. If you don't get this slide, not a problem at all. Another way to think about delta V for a whole revolution. Suppose several instantaneous velocities are recorded. These are shown as tangent lines below. So in other words, this is the velocity at that point. This is the velocity at that point. That is the velocity at that point. And you could sort of do that all the way around, right? Like that. At that point on the circle, that's the velocity vector. Right? Each vector v1, v2, v3 would be the same length because the speed is the same, constant. And the value delta V would be the difference between V1 and V2. So this thing here is the change. It's delta V1, the difference between the first two velocities. And this is delta V2, the difference between the next ones. And that could go all the way around as well. Now, if we place V1 to V8 all the way tail to tail, you take all these sort of black ones that are all the way around, we place them all tail to tail. And I haven't really mentioned this a whole lot, but you might know that tail to tail is another way to show vector subtraction. Right? So these are, in fact, here's V1, V2, V3, all the way around. You place them all tail to tail, it's another way to show vector subtraction. And in this fashion, delta V1, delta V2, etc., form a circular pattern. This is delta V1, this is delta V2, this is delta V3, and so on. And if we took these velocities at not just sort of the quarter marks, but if we took them like every second or every sort of tenth of a second, we would have multiple black ones. You would have a big giant one like this, and the difference between them would not be so straight. And in fact, delta V1, delta V2, delta V3, if it went all the way to like say V360, well, it would practically be a circle. Will, you're not paying attention. Clearly. Okay? So we've created another circle out of the change in velocity vectors. I realize this is complicated. So the total change in velocity is delta Vt, delta V1 plus delta V2 plus delta V3 plus delta V4 all the way around. And because it's a circle, well, that's 2 pi r, circumference. Hang with me. I know it's hard. And what is the radius of this circle? This you know, this you can figure out. What is the radius of this red circle? It's the black ones, is it not? Which is the velocity, where radius is equal to v1, v2, v3, and v4, and all the way, as many times as you want, right? So delta vt is 2, not 2 pi r, but 2 pi v. Saved equation number 3.
So is it like change?
The total change in velocity is equal to 2 times pi times the actual velocity, because of this logic here. Okay? That's all I'm saying. It's okay. I don't expect you to get it. I expect you to go, yeah, I kind of get it, yeah. I got an idea. Okay, now I've got 3 saved equations, right? Now comes the algebra part. Okay. Yeah. Just stay with me. I know what I'm doing. I'm feeling good about this. I got it in my head. I'm feeling good. That last slide always was the one that always gives me grief. But I think I did pretty good today. Recall equations 2 and 3, which were delta Vt is equal to At and delta Vt is equal to 2 pi V. What can I do? At is equal to 2 pi V. Mash them together. Or you can rewrite it as A is equal to 2 pi V over T, and we're going to call that saved equation number 4.
So which one do you want us to write as? Doesn't matter.
You just need to be able to solve the problems, right? All I want you to do is be able to follow these steps here. And that involves putting your phone down and staying with us, Carter. Mom's busy. She can't talk to you. Oh. Go back to equation number 1. What was it? It was T equals 2 pi r over V. Do you have a sense of dread? Because this T is going in there, and it's a double fraction. I guess you could put, I never thought of that. You could put it into there. Put that. Yeah, why don't I do that? Might make it easier. I don't know. Let me work through that on my own. You're full of good ideas. Every day a new idea, eh? Okay. So here is here is that process where I said, right, this is going into there, right? So 2 pi r over v is going in for t. And what are you going to get? Can you do this in your head? You're going to get 2 pi v over
2 pi r over v.
Exactly. 2 pi v over, it's centripetal acceleration. A is centripetal, right? You're right, it kind of just became centripetal. So 2 pi v all over 2 pi r over v.
Okay.
I don't know what this is over here. What is that over there? Let's just cover that up. Now, what do you know about fractions? Can we do some canceling? 2's, pi's, you got v over r over v.
Squared.
Right. How'd you know that?
Because it's 2v.
Centripetal acceleration is v squared over r. After all of that, I've simplified it down to the centripetal acceleration is equal to the velocity squared divided by r. Hey, that's not such a bad formula to use, is it? Okay? And again, I just need you to be sort of aware that these are not sort of just made, I mean, they're made up formulas, but they don't just kind of like, well, let's use this one because we say so. Like, it's not like people have gotten together and decided, let's use this, right? This is why this is true. Yeah. Yeah. And I've actually seen that. Well, I've seen crazy mathematicians not do this, but like actually do this kind of thing, but literally fill 8 boards of stuff. Yeah, and the one time, Professor Mendelson, I had Professor Mendelson for intro calculus, honors calculus. Here's a tip for you, don't ever take anything that says the word honors in it. I thought I was smart. When I told my dad that Professor Mendelson was my professor, he says, really? He was old when I was there. And he, one time, at the U of M, they had, I think it was whiteboards. No, couldn't have been. It was like the 80s. It must have been blackboards. They had those, you ever seen those blackboards where they slide? I used to have one in metal room on there, right? Okay. So yeah, he had those sliding boards. So we had 4 boards, right? He made a mistake on board number 1, and he was so old and couldn't hear that we couldn't get his attention. We were like, "You made a mistake, right?" And he just kept going. So we all just put our pens down, closed our books, and just sat back and watched the show, right? And he went like for an hour, got to the very end, and went, "Oh, I must have made a mistake somewhere." We had to do it all over again the next day because you couldn't get a hold of him. And another time, I'm sure he was a wonderful man. He was getting pretty old. The floors in the building were all the same. So if you got off on an elevator, if you didn't look at the door numbers, you wouldn't know if you were on the 3rd floor, the 4th floor, or the 5th floor, right? So, and all the rooms looked exactly the same. He got off on the wrong floor, walked into the room, started teaching. It's the wrong floor. We all sat and waited for him on the floor below and never showed up. Finally, we just left, right? He's like the next day, "Where were you guys?" I'm like, "Where were you?" Oh, he says, "I might have got off the wrong floor." That's probably what happened. Oh, he was the stereotypical senile old professor. Yeah. Lots of fun though. Lots of fun. Okay, and I shouldn't talk about him like that. He was a wonderful man. I think he was a distinguished professor. Like he was pretty. And if you look him up, I looked him up on Wikipedia once. He actually won several awards, but he was kind of past his prime by the time I got him. Yeah. So, v is the velocity in meters per second. R is the radius in meters. A is the centripetal acceleration in meters per second squared, and T is the period in seconds. Now, what have I got over here? And please let me see if I can figure it out. Oh, I know how this works. Okay, I know how this works. So what I do over here was I take this and I pull the v off, because when you multiply, right, you can, like, I don't have to go 2 times pi times v divided by t. I could go 2 times pi divided by t and then times v, right? Order of operations. So all I've done is I've taken the v off here, right? And then I've taken, because v is equal to 2 pi r over t, I've taken that and plugged it in for v there, and you get 2 pi t times the v, which is 2 pi r over t, and you end up with 4 pi squared r over t squared. That's how you do it.
So wait, what is the point of that?
It's just, these are equivalent.
Why would you do the way harder one?
Well, you would do the way harder one if you know the period and not the velocity. That's why. Okay? So they are equivalent.
Should we write out the way harder?
Yeah, you should. You're gonna want it. You need them both, because there will be situations where you don't have the velocity and you have the period, right? Now, please note, this is important. Area of a circle, pi r squared. Centripetal acceleration, 4 pi squared r. Easy mistake to make. Make sure you got it down right now, correct. Because I've seen cheat sheets where it says 4 pi r squared. Okay, it's 4 pi squared r. And even when you're writing it, because you've written pi r squared so many times maybe in your life, you write 4 pi r squared, right? So just be careful. 4 pi squared r over t squared. Remember when we were talking about that letter K?
Oh, yeah,
We still got to figure that out.
forgot about that. That was the point of it.
That was kind of the point. I think there's one more step before I do that, though, if I'm not mistaken. I just remembered. Yeah. Oh, no, I'm wrong. What was our predicted formula based on the experiment? Let's go back. Yeah, I know it was. I was kind of doing for dramatic effect. Well, it was A equals KR over T squared. That was our predicted one based on our shapes of graphs. And we derived 4 pi squared R over T squared. So what's K? Well, like predicted, pi was involved, 4 pi squared. You have to admit there's a certain sense of satisfaction to be able to do that, don't you? No?
I don't really understand.
You don't get any satisfaction from that?
No. Yes, satisfied.
Is she mocking me?
No, I'm actually saying that they were singing it.
Oh, you're singing it.
I was doing the first one.
Oh, yeah? That's your squirrel?
I feel angry at 11.
Oh. Okay, now, last little bit here, because we quite often talk about centripetal force, let's see how this relates. It's a one slide thing, it's pretty easy, right? So given our two new friends, AC is equal to V squared over R, and AC is equal to 4 pi squared R over T squared, if we want centripetal force, F equals MA, both of these are A, so FC is equal to MAC. So how do I make these into centripetal forces? We simply add M to the formulas to turn them into an FC, right? So if I don't want centripetal acceleration, I want centripetal force, I have to put a M in there. And if I want centripetal force here, I have to put an M in front of that one. Okay? So I'm taking the A's and plugging them into F equals MA is what I'm doing. And what do you end up with? Those ones there. Those ones. Yep. FC is equal to MV squared over R, and FC is equal to M4 pi squared R over T squared. Yes. I get it. I do. I understand. Like if I haven't been through this many, many times, like I have to remind myself, this is the first time you've seen it. I've been through this probably, I bet you 40 times in my life. Well, 20 years of teaching twice a year, right? Probably close to 40 times. I still get a little bit sort of nervous about it because I have to stand in front of you and make it look like I know what I'm talking about. Today I felt pretty good about it, so that was good. Last semester I did. I felt lousy. Remember those days? Remember when you had V equals D over T and they showed you the magic triangles?
Remember when we just had those easy formulas?
Yeah. Right? This is why I yell at kids for not using or to not use the magic triangle. Because you try and come up with a magic triangle for FC is equal to M4 pi squared R over T squared. Yeah, it is. It's like a rhombus or something. I don't know. It's not possible, right? You got to know your algebra. You got to be able to do that solving and that crossover stuff.
Okay, what is this magic triangle thing? I've never heard of.
I'll show you sometime. It only works for 3-letter formulas.
Yeah, we're doing
Yeah.
like number Avogadro.
Avogadro,
Avogadro
6.02 times 10 to the 23.
negative 20.
No, I don't. No, I don't think so.
It's not 6.02 times 10 to the 23.
Yeah, that's how many
But it's a decimal.
moles in a molecules in a mole, right?
Moles in a mole.
Yeah. See, I remember that stuff.
Last
Avogadro.
year's was on.
And I haven't done chemistry for a long time. I had a sweater like that once. Yeah, I had one of those as well.
Where one of those on my
Yeah, I don't think I can.
sweater vest?
Yeah, but not just a sweater vest, but the
Yeah,
what's that shape called? Yeah.
diamonds.
No, there was a certain that was called a certain style. I don't remember what it was now.
There's socks.
Yeah, yeah, socks. Argyle, right? Argyle vest.
Socks, Argyle.
There you go. I know way